Thank you. Test? Can you hear me? All right. All right, so welcome everyone to this talk I called Attacking Edge for the JavaScript compiler. So just some quick words about me. I'm 24. I started in security by playing CTF with the Eat Sleep on Repeat team now about 3 years ago. And I quit my job to do VR full-time in last year, and I've mainly been doing JavaScript engines, specifically JIT compilers. And this is my Twitter handle. I'll release everything, exploit code, slides, right after this talk, and I'll announce it on Twitter. So the agenda for today, I'll quickly, one slide to introduce what is ChakraCore. Then we'll do a primer about JavaScript engine. So if you have no experience with that kind of program, I think it will be good. Then we'll do some ChakraCore internals, and then we'll dive into the meat of the subject, which is just-in-time compilation of JavaScript, why it's a complicated thing to do, and then we'll talk about Chakra's JIT compiler specifically, and then we'll analyze and walk through an exploit I wrote for a JIT bug that led to remote code execution. So quickly, what's ChakraCore? So the default browser on Windows 10 today is Microsoft Edge. The JavaScript engine inside it is called Chakra. ChakraCore is basically the open source version of Chakra, so it's like 95% of Chakra. You have a few things that are not open source, like the COM APIs, the edge bindings, and everything. ChakraCore is available on GitHub, and it's written mainly in C++. And yeah, that's about all we need to know. So a quick primer about JavaScript engine. So what's the JavaScript engine? So JavaScript engine is basically something that implements a dialect that conforms to the ECMAScript standard. These days, if you take the major JavaScript engines, they will be made up of these 5 components roughly. So you have the parser, it's the entry point. Basically, that's you give it the path to your file or the source code. It passes it, produces an abstract syntax tree and a custom bytecode. That bytecode is then fed into the interpreter, which is basically a virtual machine. It just runs that bytecode. To do that, it relies on what we call the runtime, which basically provides all the basic data structures, standard libraries, built-in functions. Of course, you have a garbage collector because you don't have to deal with memory management in JavaScript, and you have one or many JavaScript compilers. And more on that later, as this is the subject of this talk. But basically what they do is they take the bytecode and magically produce optimized machine code, and we'll try to demystify that. So now quickly about some of ChakraCore internals that we'll need throughout the talk. Everything inside a JavaScript engine is what you can refer to as a JS value. So inside Chakra, everything has the same type, which is var. It's just an alias for a void pointer. ChakraCores use non-boxing, so it's a clever trick to encode some kind of time information alongside the value for your JS value. So if you take the integer that's x 41414141, it will be represented internally with the 48-bit set. So as you can see on the right, and same thing if we take the double that's represented in hex as 41414141, you can see that the upper bits are set to FFFC, which is basically a tag that tells us this is a double. You should treat that value as a double. And what that means for us is if the upper bits are cleared, we're basically dealing with what should be a valid pointer, which will point to a boxed object for your more complicated stuff. So those things are commonly called JS object. So JavaScript objects are basically a dictionary, so it's just a simple collection of key value pairs. The interesting thing is that in all engines, basically the object doesn't maintain its own map of property names to property values. They all do the same thing, which is the object basically only has the values, and it points to some kind of structure. In Chakra, it's called a type, which basically describes that object's layout. It allows for 2 things, 2 really nice things. The first one is you save memory by sharing the type across objects, and you also allow for an optimization called inline caching that I'll explain later on. And in Chakra, we have 2 main layouts. The first, most standard one is you create an empty object, you set property X, property Y. If you look in memory, you will basically have the virtual table pointer, then the type that I talked about, and basically this aux field, which is basically a pointer that will point in memory where your property values will be. So here you can see that it points to 414141 and 424242. You also have another layout, which is for scalar object. So internally it's called object header inline, where basically instead of using that extra indirection, they will store the property values directly inside the object, which is also a trick that you find in other engines. So basically, property access, what it looks like, as I said, the type is basically this magic thing that is able to tell you where your property is. So in Chakra, basically, a property name is represented as a property ID. The type is basically able for an object to map a property ID to an index into the aux slots array. So basically, when you fetch property a.x, as can be seen on the left, you basically end up with this call chain, and basically the type is magically able to tell you, oh, this is at aux slots at index 0, and it will return that value. A few words about JavaScript arrays. So interesting to know, like in the standard, JavaScript arrays are only defined as an exotic object, which have a special property called length. All the engines basically have some different storage mechanism to allow for optimizations. Chakra uses a segment-based implementation that we'll see an example of on the next slide. And you basically have those three main classes to allow for storage optimization. So the first one, JavaScript native int array, basically like everything will be stored on 4-byte and the values will not be tagged. Then you have native float array and JavaScript array where you can have anything basically. So to highlight the segment implementation, like I have a simple scalar array, 1 to 3. In memory, basically the object will point to this segment, which has left basically says what is the index on the left, so it's 0 here. 3 elements, and the thing is allocated up to 6 elements, so that's what size is. And we can see that next is 0, because we don't have a next segment. Now if I set a property to a super high index, well, not super high, but like 100, you probably don't want your engine to allocate memory for, like, you know, when you want to store only 4 elements, you don't want to allocate 100 times the size of the elements that you're trying to store. So Chakra uses segment, where basically it will create a new segment where the left index will be 100, and then basically you can chain segments like that. So yeah, that's it about the internals. It's really brief, but that's all we will need throughout the talk going forward. So now we'll dive into JavaScript JIT compilation and the problematic associated with it. So the goal of JIT compilation is to generate highly optimized machine code. Of course, the upside to that is that you get much better running speed, but you have the problem of higher startup time because compilation takes time, and JavaScript also doesn't have type information, so you have to deal with that somehow. So in practice, what you get is your execution starts in the interpreter, and if something gets called repeatedly, so a function, it will be basically scheduled to be JIT optimized and compiled down to machine code. So we'll see with examples. I'll try to explain a bit how JIT compilation is done. So here we have a simple function that basically gets 2 parameters and does the addition on the 2 and returns that. And I think by now, most of you have seen some memes about JavaScript addition being quite nasty. If you look at the standard, this is basically what the standards say addition should be on the right. So you see you have a lot of stuff. And basically the realization is if we have this function addition and we only call it with integer values, we probably want something that looks close to what I have on the right, which is assuming the 2 parameters are in RDI and RSI, we just like add the 2 in the return register, and then we return. So 2 assembly instruction, but we don't have type information. We don't have anything that tells us this is going to be integer values. So the solution to that is called profiling, and basically whenever you run into the interpreter, you will basically gather profile information about the type of parameters and such. And that will allow you basically to do some optimization. And the idea is we generate optimized code based on what we profiled so far when we JIT compile a function. So here I call my function in a loop 1,000 times. I only pass it integer parameters, this variable I, which is the induction variable, and an integer constant. So basically the interpreter will gather profiling information, which is, oh, this is integer parameter all the time. I haven't seen anything else. And the idea is that the JIT compiler will generate code that we'll first check that the things are in fact integer values. And if so, then we can generate super optimized code based on the fact that this assumption will basically be true. So here I have another example to introduce something I talked about previously. So here I just have a simple function called getX, which fetches property x on the object that you give it to. And same thing, I repeatedly call it in a loop with the same scalar object. So it will actually be a different object internally, but the layout will be the same, only one property x that will be at the same offset inside the object. And the same realization here is that we don't want to actually compile down the whole object lookup, looking through the type where that property is, because then we don't actually gain anything from the interpreter. That's what the interpreter already does. So the solution here is, once again, we'll collect profile information on the type of the object, and we will assume that it will stay like that going forward, and then we'll be able to use direct memory index, and this is what is called inline caching. And if the assumption does not hold, we'll basically fall back into the interpreter. So that takes me to introducing two key concepts that are used in JIT compilation. The first one is so-called slow path. So basically, as I said, the JIT will basically have to make assumptions and check that these assumptions are actually true. And if something is not true, then the JIT code might have to fall back into the interpreter via something that's called a slow path. So the bad news is that you get a performance hit for that. But you also have the good news, which is the JIT code actually accounted for that. So sure, for that operation, you will run slower because you have to go back into the interpreter, but you will come back into the JIT function going forward. So it's not too bad. The other key concept is called bailout. And here basically is that sometimes if you have an assumption that's not true, the JIT code is completely unusable. So that would be true, for example, if you profile something that takes an integer value, and all of a sudden you give it a pointer. You will do some tag checks, bit stuff that will basically clobber the pointer, so you will most likely crash at some point. So in that case, you just have to, you just have to give up and say, I can't deal with that. And basically, you have to run the rest of the function inside the interpreter. The big downside here is that you have a big performance hit because bailing out is a non-trivial process. There are a lot of things to do and to do properly. And I guess the upside is that you maybe never realized that this was actually going on inside your engine. So it's a pretty good testament to the development team. So to summarize, JIT compilation, as I said, of JavaScript will rely on profile information. This is basically what gives you some kind of type information that you collect during the execution in the interpreter. Highly optimized code will be generated based on those assumptions, on that information. And the key takeaway is that your JIT code has to be responsible for checking that these assumptions are actually true and be able to deal accordingly when they're not. And basically, you have problems when you can trick the engine into, like validate some kind of assumption or, bypass some checks and stuff like that. So now I'll talk specifically about Chakra's JIT compiler. So basically, the Chakra JIT pipeline, you have an interpreter. As I said, every time you call a function, it will keep track of how many times that function has been called. This is a simple counter. Past a certain threshold, basically that the interpreter will say, oh, this is being called a lot, let's JIT compile it. So it will basically change the entry point to something that will start JIT compilation. What happens in Edge is that actually you have the JIT compiler runs out of process. This is mainly so that the renderer process can benefit from arbitrary code guard. If you want to know more about that, check SARS talk at C3, he talks about it briefly. And when code generation is done, basically you change the entry point to the native code address. So the next time you will actually call the function, you will just jump to the JIT generated code. Chakra has a two-tier JIT compiler. The first one is called simple JIT. Second one is called full JIT. We'll solely focus on full JIT because this is the one that does the most optimization, so it's the most interesting one as a security researcher. It basically operates on a CFG and a custom intermediate representation that's being generated from the bytecode. So it's not uncommon that the JIT compiler will actually transpile the bytecode to something that's most suited for JIT compilation. That's because the bytecode is, of course, optimized for the interpreter, which might not be the best thing for the JIT compiler. So the main steps of compilation in Chakra, first off, you build the intermediate representation from the bytecode. You have an inline phase. The reason it's done so early is that inlining stuff allows for further optimization. So if you look at other JIT engines, you will see that inlining happens pretty early on. Then you have this flow graph build phase, basically builds the CFG. And then you have this global optimizer phase, shortened as global phase, which is basically where most of the magic happens. And we'll talk about that in details going forward. And then that's it for what is architecture independent. Going forward now, everything is kind of machine dependent. So like the lower phase will basically basically lowers the IR to machine-dependent operation, and then you go lower and lower up to the point where you actually write instructions to memory. So as I said, the globopt phase is what interests us the most, especially the full JIT one, which we'll talk about in details now. So I have two examples to show you how it looks like. I realized this morning that if you are in the back, it might be a bit hard to read, especially at the bottom. So you'll have to take my word and hope that I don't say anything stupid. So here, I'm taking the same example that I had previously, which is like a function that does a simple addition of two parameters x and y, and I keep calling it with integer value. So at some point, it will be JIT compiled. And now we'll basically look at the assembly code that's generated. So here I have the assembly code. This is something that you can do from a built Chakra binary. It's some kind of high-level assembly, so you won't see a lot of like registers and stuff. You will see like this symbol S, and some integer. So that gives you some kind of like high-level assembly that you can look at to see what's going on. So here, highlighted in red, I have like the intermediate representation of the instruction that we're currently looking at. We can see that it does basically something S0 equals add A of S2 and S3, and it looks pretty much like what we would expect, right? You know, simple addition. S0 is the symbol for the return value. S2 and S3 are like the parameters. So nothing too crazy here. The interesting thing to see, though, is that in between brackets, we have something that reads likely can be tagged value int. And this is basically our profiling information. Like the JIT compiler basically annotates the thing saying, at this point, this thing can likely be a tagged value of type integer, because this is what the profiler tells me. So the first thing it does is this short sequence of assembly instruction basically checks that both x and y are integers. The way it does that is that, if you recall from the first slide, integers will be represented with the 48-bit set, so it just like shifts right the two values, ORs them together, and basically compares them to this constant x10001. So it's a Qt optimization to check that both are integer at the same time. And if that thing doesn't succeed, so I don't have the jump highlighted, that's a bit unfortunate, but you can see that it jumps to this label L4, which is referenced further down as well. And here in this label L4, we basically there's a bunch of instructions, but the interesting one is at the bottom. It does like move up at full and calls that register. And that's basically the slow path I told you about previously. We are not dealing with tagged integers, so the JIT optimized code that we generated will actually be wrong, and we cannot use it. So we have to go back into the interpreter, which will do like the whole addition logic. And here we have the code if the assumption actually was true, which is that the two things are actually integer, and we can see that it's a simple add instruction in assembly. And check for overflow, because everything is within the 32-bit boundary. And then we just set the tag bit again, and that's it. We've done our addition. So the takeaway here is that basically, if the assumption actually was true that we are going to deal with integer parameter, we don't actually run that many assembly instructions, like 7 or 8, give or take, maybe 10. So that's pretty fast, and that's how you get basically fast code inside the browser. So I have another example here. Same thing, it does the addition, but this time it will actually add two object properties together. So we've seen the addition. Now I want to highlight property access, how it looks like in Chakra when it's optimized. So once again, I have this function, and I only call it with one type of object, which is the scalar object sorry, with x and y properties. So the profiler will only see that one type, and the JIT compiler will optimize the function for that particular type. So now let's see how it looks like. So basically, same thing. The first thing we do is we check if we're actually dealing with a tag value or not. So if any of the upper 48 bits are set, we are dealing with a tag value. And since our code is optimized for a pointer, we absolutely, we have to bail out. So this is the thing you see. Basically, shifts the value right by 48. If the thing is 0, we can go forward. But if it's not, then we call save all registers and bail out, because the code will expect a pointer, and you give it something that's not a valid address. So, you're going to crash. And we want to avoid that, of course. Now, the interesting thing to look at is that initially the thing is marked as likely can be tagged value object, which is why I talked about previously, the profiling information. At this stage, the JIT has some hint about what the variable could be, which is like it can be an object, but we don't have any guarantee because we didn't do any check on it. But now that we reach that instruction, we know that the thing we just did was basically checking that the thing is an object or not. or checking if it's a tagged value to see if it's a pointer or not. And here we can see that the symbol information has basically been updated. So the thing is not marked as likely can be tagged value anymore, it's marked as being likely object, because we know we are dealing with a pointer going forward. So now the next thing we do is basically a check to see if we are dealing with the type we profiled during the profiling phase. And once again, we have a slow path. If we are not dealing with the type we profiled, maybe that type for some reason is a different type but has the same exact layout, so in which case the JIT code will be valid. So this is what you see here. It will call something called check if type is equivalent. If that thing returns true, we'll actually go forward in the JIT code, but if not, we'll actually bail out, because then our code is just garbage and we'll do bad things. And now we get to the actual property access. And here, this is what I talked about, inline caching. You can see that, so this is basically O.x that you're looking at. And you can see that it just does a straight memory access at offset 16 of the pointer, because this is where property X will be. And now we have the access of property Y on O. And here we can see that same thing. It does an access at offset 24, because this is where property Y will be. The interesting thing to note is that we don't redo the checks that we just did, because we know that in between property access of X and property access of Y, then the object hasn't changed, so we don't have to redo the checks again. So yeah, I hope it sheds some light on some core optimization that are done in the thing. Now I'll try to explain a bit how Chakra is able to do all that magic. So as I said, the magic happens in the global optimizer. It's a 3-pass process on the control flow graph. So you have one backward pass, one forward pass, and another backward pass. The 2 backward pass, even though different, are actually implemented in the same code base, which is a bit confusing. It's about 9,000 lines of code. And the forward pass is the most interesting one that performs most of the optimization, and it's about like 30,000 lines of code. I put the file names in there if you're interested to check out on your own. And the whole thing starts in the glob optimize. So if you want to look for the entry point, this is the function you want to look at in the code. So the backward pass is the first thing that runs in the global optimizer. It's not the most interesting for a security researcher. The algorithm is pretty simple. You go over each block backward. For each block, you go over each instruction backward. Information is gathered for each block. And basically, every time you start processing a new block of the CFG, you have to merge information of the predecessing block, the ones you treated already. And it can perform some simple optimization, like instruction rewriting, some kind of constant folding and stuff like that, but it's not really interesting in terms of security bugs. And yeah, that's about it. It's not super interesting for us. Now the forward pass, which is what we really care about, the algorithm is the reverse, so you go over each block of the CFG forward. For each block, you go over each instruction forward. And basically, for each instruction, the JIT compiler will call about 40 to 50 functions that will only deal with certain instructions. So if you look at the code, you will see that there are switch statements everywhere. And same thing, information is gathered for each block. And whenever you start processing a new block, the first thing you do is you merge the information that you have of the predecessor block, of the new block you're processing. And that will actually perform most of the magic that will lead to the optimized code we just looked at. So here, once again, we'll run through an example to kind of give you a sense of how things are done inside the JIT compiler. I have the same function addition that adds 2 object properties together. And on the right, I have the intermediate representation after the backward pass. So right before we run the forward pass, this is what we have. We can see that it's pretty much what we have, we can correlate pretty easily to what's in JavaScript. We just do 2 load fields, so it's just like property access. We load O.x and O.y, and we add the 2 together in S0, which is the return register. Now, if you dump the intermediate representation right after the forward pass, you have this thing that's totally unreadable. It's actually redacted, believe it or not. It's even more cryptic than that, in reality. And basically, the only thing I want you to take away here is that somehow the whole thing has been changed. Everything has been enriched. We have more annotation. We have a new instruction and stuff like that. And the question now is, how did we get there from the previous intermediate representation? So, as I said, like in the forward pass, you'll go over each instruction forward. So, sorry, each instruction will basically go through this optimized instruction function. And as I said, this thing will call about 40 to 50 functions, passing the instruction. And some of these functions will not actually do anything, and some of them will do something. So at some point, optimized instruction will call this thing called opt tag checks on that instruction. And if you look at the code, you can see that you have a switch statement with a case for when the opcode is a load field, which is what we have here. So this function actually is supposed to do some things when we have this instruction. And now if you look at the code, you can see that it will do some stuff on the right. So the first thing, it just retrieves the value information that you have for that block, for that particular thing. And then we have an if statement, which is if value type can be tagged value. And the first, like at this point, this will actually return true. So we'll take the if statement. And now it will do two things. So the first thing it does, it actually creates a new instruction, which is bail on not object. And it will insert that instruction before. And then we can see that it actually updates the value type. Because since we inserted a bailout instruction, we now know that going forward, the thing cannot be a tag value anymore. So we update the type information. So the JIT compiler now knows, oh, this thing is not, I don't have to deal with the fact that it can be a tag value because I know it's not. So now, we keep running, and then we start processing the next instruction, and we'll take the same code path. But the thing is, this time, we updated the value type. So now the if statement will actually return false, and you will run maybe different code or that sort of stuff. So it's a really minimal example, but it's kind of to give you an idea of how things are done. Basically, you call a bunch of functions. Based on what you have, you will either refine your type information, or you will actually have to loosen it. And that's what the JIT compiler does. Based on that, it will be able to do more optimization, or it will actually have to insert additional checks. So there's, of course, a lot more happening than that. This is just to give you a rough idea. If you look at the code, I hope this actually kind of gives you, some idea of what's going on and what to look for. So now I'm going to introduce two key concepts that are used in Chakra. So symbol liveness, which is, so basically a symbol in Chakra is something that basically represents a variable or some kind of internal fields. And basically, they have this concept of liveness, which is, if we take my function, which basically adds two properties together, o.x and o.y, then if I call the function with that particular object in the loop, o.x is basically at offset 0 in the aux pointer, and o.y is at offset 1 in the aux pointer. And these days you expect your compiler to generate something that will actually load the aux pointer only once and access the two properties directly instead of loading the aux pointer, accessing the first property, reloading the aux pointer, and accessing the second property. So in order to do that, Chakra has this mechanism, which is basically symbol liveness, which is when it will optimize the property access of o.x, it will actually see that the thing will trigger an aux slots load, and will actually set the symbol associated with it as live going forward. What that allows the JIT compiler to do is that when it treats the next instruction, it will look if, is that symbol live actually or not? And since it's live, it knows, okay, I don't have to reload it. The thing is live, I can use it, it's valid at this point. But now you have the counterpart to that, which is, what if we slightly change the function so that in between the access of property X, we have some operations, and then we access property Y. And what if those operations actually trigger the aux pointer to be reallocated? So that would happen if you had like a whole bunch of property. You have to reallocate enough space and copy the properties. You don't want to use the previous value of the aux value because now it would point to free memory, or maybe you want to look for that particular situation if you're looking for bugs. So the mechanism that allows the JIT compiler to deal with that is something called the kill mechanism. This is Chakra lingo. If you look for the string kill in the code base, you will find some occurrences to it. And basically, in that case, where some operations might actually cause the reallocation of the aux pointer, then the JIT compiler has to kill the symbol associated with the thing that might be changed. And if you look, it's basically the same mechanism that's used throughout the JIT compiler for all kinds of type information. And if you look at some of the bug reports from like LookYart or Sorry My Bad, especially with arrays, that's basically where like the JIT compiler actually basically failed to kill certain type information under certain situation. And that's basically what led to those security bugs. So the forward path, it was probably a lot to take. Still, seems simple enough. Well, the truth is, all the functions I gave you were really simple in essence in terms of like the CFG, because you only have like one block and you basically have only one path through the CFG. But if you start adding like some JavaScript constructs such as loops, conditional statements, try catch, and all that sort of stuff, then you you complexify the CFG a lot, and you have to deal with that. You also have a lot of different things to keep track of, so variable aliasing, what to restore in case of bailout. The JIT compiler also has to model the behavior of slow paths, so you don't want your JIT compiler to say, I might call into the slow path, but this won't change anything, and then the slow path changes something internally, so that could be one place to look for bugs as well. You have range analysis for bounce check removal, always some bugs there, and much more things to keep track of. So a quick slide about loops. As I said, loops are kind of, you have to deal with them. As I said, the algorithm, basically, you go over each block once and you treat it, but if you have loops, you have to be a bit smarter than that. So, because if you think of a loop in terms of how it represents in a control flow graph, you will basically have, the first time you run into a loop, you come from one code path, where you have certain information that is true, and then all subsequent iterations will have that information as well as the information that's true from the loop package, because you will have run the loop body once, and the loop body might change some information that you thought was true coming into the loop. So you basically have to run through each block twice. Internally in Chakra, it's referred to as the loop pre-pass, and things have gone wrong due to that. So yeah, I have a simple example to highlight the problem. Here we have a function, doesn't do anything meaningful. It actually won't crash, but it will return undefined every time. The interesting thing to look at here is that I have this object that I declare as a scalar object, so the JIT compiler will actually know its type. And basically when we access a.text and we put that into the ret variable, the JIT compiler might be tempted to say, oh, I know the type, I can just use inline caching, like directly access the memory where the property x will be. But here we have to see that there is this instruction that is A++, and A++ in JavaScript will actually type specialize A. Going forward, A will now be a number, so it's not an object anymore. And if your JIT code actually doesn't account for that, then on the loop package, you will treat the thing as a valid pointer, and you're going to have bad surprises. So that's basically where the algorithm of the loop pre-pass comes into play. You will do a first pass on the thing to basically get all the type information and what's basically going to happen to be able to optimize the thing accordingly, knowing that the loop body might change some stuff or not. So once again, that previous example, super nice to deal with. You don't have complex construct inside the thing. Things can, of course, be way trickier. And 3 days ago, Microsoft issued the patch for those two CVEs that are reported and are basically bugs related to that. So if you can look for those CVEs in the ChakraCore GitHub, and you will see the patch for those bugs. I don't have time to talk more about it, but if you want to check it out, go for it. Or you can ask me questions after the talk. And now the dead store pass, which is the last thing that runs in the JIT compiler, is the same algorithm as the backward pass, so you go over each block backward, over each instruction backward. And mostly it removes redundant code, so like redundant type checks and that sort of stuff. It's not like, at least in my experience, I don't find it super interesting in and out of itself, because all the bad decisions that are taken in the dead store pass are basically consequences of bad decisions that you took in the forward pass. So if you want to look for bugs, while Chakra still has a bug bounty program, go look at the forward pass. Okay, so now I'll run through a JIT bug that was enough to get RCE in Edge. And yeah, we'll try to break it down together. So it's the CVE ID. It's a bug I reported back in June last year. I found it with fuzzing. I won't talk about the methodology here at all. I'm going to talk about that with Niklas at Infiltrate. So if you're interested in that, check out the conference or the talk once it's released. It was fixed in August last year and basically relies on mismodeling by the JIT of internal changes. And we'll shed some light on that. So here, basically on the left, I have some JavaScript code. And if you are to run that on a vulnerable version of Chakra, you basically can observe the following crash, where it's basically trying to move whatever is in RBP into a memory location. And if we look at the values of the register, RBP is actually the tagged integer 1, which we have on the left with O.E equals 1, so that seems to be that. And if we look at the value of RAX, which is used as the base address of our buffer, we can see that it's set to the tag value 41414141. And we can actually see that on the left, we set some property to x41414141. So it looks pretty suspicious. So basically what that tells us, if you're a bit familiar with Chakra, which I hope you are now, is that somehow the oxlots pointer of our object has been corrupted with that value x41414141. So when we now try to write to property o.e, we have to go through the oxlots pointer, and that fig is a tagged integer, it's not a valid address, so we are going to crash, and this is exactly what we see here. So, quick refresher. Maybe when you saw that, you thought, oh, maybe things can go wrong with that sort of stuff. When you declare a scalar object, you have to keep in mind that you don't use the oxlots pointer, you actually inline the properties directly inside the object, where you would have the oxlots pointer under normal conditions. So this is important to understand the bug. So now let's try to break down what happens in our trigger. So I have this function called opt, and I call it repeatedly inside a loop with the same scalar object every time. So as we've seen, this is basically to JIT optimize the function for that particular object layout. So the JIT compiler will optimize the function with only one type, account for that type, and so forth. Now I access properties, o.b and o.a in the inline function and the opt function. This is not super important, just need that to have the symbol live so you can have the optimization to take place. Then in the inline function, I add a new property called e. And now basically in a loop, I repeatedly call the inline function and I set property a all the time. So it's not anything meaningful. I doubt that you're going to write JavaScript code like that because I wouldn't see the point, but it's not ludicrous either. Like, it doesn't rely on any kind of weird features like getters, proxies, or anything. So we would expect the thing to run fine. And basically the key to understanding debugging is how basically things will differ when I call the thing with like a scalar object that has 3 properties and a scalar object that has 4 properties. So let's look at that now. So now I have a scalar object called a that I declare with 3 inline properties, a, b, c. And if I look in memory, in WinDBG, this is basically what we have. And we can see our property A, B, C, where we expect them to be, so directly inlined inside the object. So now I add a 4th property, A.D, and I look in memory again how it looks like. And we can see that basically the second pointer has changed. This is the type pointer, so it has been updated because the thing has now a different type. And we find our property D, which is x4444, where previously there was 0. So nothing too crazy. Like the key takeaway here is that basically we added a new property, but the object layout actually didn't change. We're still using this object header inline layout. Now what happens with 4 properties? So here I have 4 properties, A, B, C, D, and I look in memory how it looks like. And we have the same thing. We can find our 4 properties directly inline inside the object. And now I add a 5th property, A.E, to x4545. And now if we look into memory, we can see that a lot of things have actually changed. So we have the type pointer that has been updated as before, and we can see that where 4141 and 4242 were, we now have like what looks like a valid pointer, and a null pointer. Then we have our properties 4141, 4242 that somehow have been moved by like 16 bytes. And if we dereference the pointer that we have at the 3rd keyword, we basically find the rest of our properties. So, x4343, 4444, 4545. And what we're looking at here is that famous oxlots pointer. So the key takeaway here is that going from a scalar object with 4 properties and adding a 5th property, we actually completely modify the object internally. Like, it switches from that object header inline layout to the regular layout. And this is basically the key to understanding why this thing is actually buggy. So now, like, the question is, when we set that property O.E, which effectively adds a new property to our scalar object, what happens if the JIT compiler somehow fails to account that this might change the layout, and therefore omits the type check, saying, oh, this won't change the layout, I don't really need to check if the thing is of a certain type, it will still be inlined. Well, this O.A equals 414141 will basically end up writing where O.A previously was, which is directly inside the object. But now we are using an oxlots pointer, so we basically overwrite a pointer. So yeah, that's basically the trigger. I hope it was kind of easy to follow. So now let's take a step back. So the primitive we have is we are able to overwrite the oxlots pointer of an object with a value from JavaScript. So there are limitations associated with that because, as I've introduced, you can't generate a valid pointer value from JavaScript. You know, any integer that you write will be tagged with the 48-bit set, so that's not a valid address. So that goes for either setting the pointer or actually writing a value in memory. So we need to further corrupt other objects. And if you've ever done browser exploitations, you know that array buffers are probably the greatest gift that was given to us. So we'll just use that. So yeah, now I'll walk through the exploit. The code will actually be released, so try to follow along, but everything will be released right after the talk if you want to check it out. So the first thing I do right before I call my trigger is I declare this global object, obj. I just set 9 properties to it, and I declare a global array buffer. So nothing crazy. And now basically I use my buggy function. And here we can see 2 things that have changed. Instead of setting a to x414141, I set it to obj, the global object. What that does is that creates the memory layout that you have on the right, where you have the local object O, which Oxford's pointer actually now points inside our global object. And now when I execute O.e equals target, I basically make my global object obj point inside the array buffer itself. So all of that basically to achieve that memory layout, which we have a global object whose Oxford's pointer points inside a target array buffer. And an array buffer is really nice because there's this buffer field, which is basically like the pointer to where memory for that array buffer is basically. But we still have the same issue, which is we really want to corrupt that buffer property, but we can't actually set it to anything arbitrary at the moment because we can only overwrite it with something from JavaScript. So we cannot set it to fully controlled address. So what we do now is we basically just use another array buffer object. So I declare another array buffer object called hacks. And basically by doing obj.h, what happens is I'm actually overwriting the buffer property of target to point inside hacks directly. What that gives us now is that array buffers are really nice because you can declare typed arrays on them, and typed arrays give you a way to actually read and write memory values that are not going to be tagged or anything. They are just going to be stored directly with their representation. So now by creating a typed array on target, I'm actually able to modify whatever is in hacks with the values I want, basically. And now I have full control over the hacks data. So basically with that, we can defeat ASLR. The cool thing about Chakra is that objects have a vtable pointer. So just by creating a typed array on my global array buffer and reading at offset 0, I read the vtable pointer. So that gives me the ability to leak the Chakra base address. And by reading a view at offset 7, I read the buffer pointer. That gives me a location in memory where I can put arbitrary amount of data, basically. And now with that, I can construct a read and write primitive, totally repeatable, totally arbitrary, which is really nice. This is the code for it. So basically, the first thing it does in both read and write, I write to offset 7, which basically corrupts the buffer of hacks. And now I can just create a typed array on hacks, and that will actually read and write from an arbitrary memory location. So that basically gives me full read-write, and that's enough to get RC, at least on Chakra. So I have a nice demo that's totally non-exciting, because you will just see a calculator appear. But I spent like 7 hours making it work, which is way more than I'm proud to admit. So yes, right. So I just have the Chakra built, run my exploit, and that's it. Thank you. So quick notes about exploitation. This is stuff that you are going to see in the thing. You might have noticed I didn't run the thing in Edge because exploitation in Edge is quite painful. So well played, Microsoft, I guess. Because you have to do for up, stuff like that. The cool thing though is with our primitives, which are absolute read and absolute write, even though we have to do for up, which is painful, it's mainly a matter of leaking a stack address because there's no written flow guard or whatnot. And leaking a stack address in a web browser is usually pretty easy. In Chakra, you have this a global thread context structure, which will be like at at a known offset inside the Chakra DLL, you can actually read in memory there, and you will have the stack limit, so that gives you, a stack lower bound, and you can just compute a stack address on that. This is what I use in my exploit, if you want to check it out. So yeah, demo, we did that. So in conclusion, JIT compilation is a really complex software engineering problem, especially when you don't have type information. I know it can seem hard to get into. That's definitely how I felt when I started. And my hope is that this presentation can get some people to get into it. And even though Chakra's days might be numbered, as you know, even though the implementation details will differ from one engine to another, the concepts I talked about, you will find them in every engine. So I hope you'll still get some value out of this talk if you don't intend to look at Chakra, but other JIT engines. And yeah, that's it for me. So thank you very much, and I guess we're done. I guess we have time for a question.
Yes. Questions? Preferably at the opposite end of the room.
Thank you. Great talk. It's a real pleasure to see people abuse JIT compilers like this.
Thank you.
Looking at the code, did you get any sense of whether the authors were using any kind of formal methods or some other ways to convince themselves of the correctness of this code?
No.
So it's just straight up hacked,
yeah, it's just
non-generated code.
Yeah, like JIT compiler is hard. I don't get the sense that there's much formal verification of stuff like that going on. I think at the end of the day, like these people working on JIT compiler are compiler engineers, not security engineers. So yeah, I don't know how much is done inside Microsoft in terms of Chakra, but as far as like the development team is concerned, I don't think so. But I could be wrong, but that's not my impression that they were doing in kind of that stuff.
Thank you.
Anybody else?
So what's going to be your next target once Chakra is dead?
It's still a touchy subject. No, like, I honestly don't know. I'm still really interested in JIT compilers. I don't think I've explored everything there is to explore in that field. So probably another engine. I'm not set on which one yet.
Have you looked a bit at TypeScript and stuff like that, and how it impacts the code that the JIT generates? Is it better or stuff like that?
Not at all.
Okay, if there's no further questions, let's wrap it up, and then we see each other again at coverage guided fuzzing for USB with Syscaller at 6:30.